So a chemical change, right? So right here with the chemical change, what we have going on is basically you have a transformation of reactants to products. And just know that for these reactants and products, basically what's happening is you're having a chemical rearrangement of bonds. Right, so if we have this, an example of one of these chemical changes is, just to provide a context, right, when you have CO2 coming out of a volcano, and it's being added to H2O, those two things come together to form carbonic acid. Now I told you, right, it's a chemical rearrangement of bonds. If you look at the chemical structure of CO2, it looks like this. It's a C, it has two double bonds coming out of each side. For H2O, you have an H with an O. Now, when you form carbonic acid, what you have is you have a carbon and you have this. So what you'll see, right, is that if you consider the Lewis dot structure of CO2 plus H2O forming carbonic acid, you can see that there's a difference in what carbon dioxide looks like and H2O combining, it looks different than the carbonic acid that's at the end. The bonds have been rearranged. This right here is a chemical change. Now, the difference between this and a state change is this, right? So a state change is usually between a gas, a liquid, and water. And what you're really changing is you're changing the association between the molecules. Sometimes it's distance, right? Distance and association between molecules. So what's happening here is you have ice, right? And inside ice, you can have water, right? And we know that with water, it's going to have a negative charge in the oxygen and a positive charge in the hydrogen. And because opposites attract, right, the negative is going to be attracted to the positive, so you have this lining up through hydrogen bonding, right? And right here, you have the same thing going on, right? So you have this nice ordering, and this is with ice. Let's say we switch over to a liquid, right? So now we have a cup of water. Right here, this is liquid. And inside that liquid, you have all of these disorganized, all over the place, water molecules. But there's still an association, right? So that's what's going on there. Now, if you go over to a gas, you have something else where you have basically this H2O, and they're very far spread out, and they're not really associating much at all. Okay? So this is a gas. So what you should consider, right, is that with ice, liquids, and gas, no matter what, you're going to have water. And there's no rearrangement of bonds. There's only a difference in the association and distance between the molecules based on if it's an ice, a liquid, or a gas. Ice being solid. So, if I were to ask you this question, this is what was missed on the exam. Which of the following is not a chemical process? And I were to ask you, okay, formation of carbonic acid is answer choice A. Formation of calcium carbonate, fermentation, or evaporation. What would the answer be? Which one is not a chemical change? That's right, evaporation, because water is still water, it's just changing state. So it's a state change. Cool. All right, so let's go ahead and move on from this. The next thing I want you to consider is the shape of an atom, right? So let's talk about the anatomy of an atom. So on the inside of the atom, inside a nucleus, what do we have? We have what two components? And I'll take a hand. What two things reside inside the nucleus? That's right, protons and neutrons. So when you look at carbon, carbon has an atomic number of 6. So that means that it has 6 neutrons, 6 protons, and 6 electrons. And just talking about the protons and neutrons, you have 6, right? And you also have neutrons on the inside too. Okay, cool. Now, where are the electrons going to be? Who can tell me where the electrons are going to be? I'll take a hand. Yes? Who can tell me? Yes.
Circling around.
Yes, exactly. So, in the empty space around, right? Okay, cool. And these are just empty spots in the next valence shell. Okay, now, what is an isotope? Who can tell me what an isotope is? So, an isotope is basically going to have different number of neutrons, right? So, an isotope, right? So, isotopes have different So let's say we had minus 2 neutrons. And then over here we had minus 1 neutron. So what you'd have in the end, you'd have 4 neutrons. And then you'd have all of these electrons on the outside. Cool. And then if you lose 1 neutron, you'd have 5. Cool, so I want you to go ahead and consider this, right? What happens to you when you go through the day and you haven't eaten at all and you're hangry, right? What emotion are you?
Annoyed, impatient.
You're impatient, you're annoyed, right? Those are all reasonable things. Those make sense. So I want you to think about this, right? When you look at isotopes, isotopes have different number of neutrons. And because of that, you're kind of talking about 2 different forms of the same thing. So when you have, your regular carbon, the one that's most likely to occur, basically, consider that someone with a full stomach, right? That's the person that they are most of the time. And now when you take on different amounts of hunger, if you're really hungry, you've lost 2 neutrons. Basically what's going on there is, let's say you haven't eaten at all and you're very hungry. This isotope is going to have slightly different behavior because now it's a slightly different molecule. So that's what we can expect to see from that. In the same vein, if you have a different type of isotope, it's going to have slightly different behavior. Okay? So isotopes differ in the amount of neutrons. The next thing I want you to consider, right, is an application. This is kind of interesting. So why would somebody care about putting radioactive glucose inside somebody's body? So we take these carbons, right, and we put an isotope right there. Now, why is that useful to us? Radioactive glucose, what's going on there? How can that be good? So what's cool about glucose is we know that as far as energy is concerned, we need that for what process? Not the heating. I heard it. Yes?
Production in, there's three. It's production in building macromolecules, excess goes to plants, and the other is for ATP.
Yes, I see what you're getting at. So, that's perfect. The one above is young. The thing that I was looking at within that was the formation of ATP. The cycle was cellular respiration. So, perfect. So basically, right, if you have cancer cells inside your body, let's say that you're some kind of medical professional, and somebody comes up to you and you're like, hey, I think I have cancer in my body. Can you tell me where it is? What you could do is you could take radioactive glucose, and you basically make all the carbons inside that glucose radioactive. And what you can do is you can put it inside somebody's body, and you're able to track where the isotope is going because it has radioactivity coming off of it. And radioactivity is fine, right? It's not dangerous. Some radioactivity is, some isn't. This one is fine, right? You're basically looking and you're tracking the glucose and you're finding out, man, all the glucose is being absorbed in this one particular spot where this clump is. What does that mean? So that means that all of the glucose is going to the tumor or the cancer, and because of that, you can kind of see where it's going. This cancer is trying to grow. It's eating up a lot of glucose, so you can use glucose to that advantage to find out what's going on. Just rip it out. There you go. Cool. All right, so the next thing we're going to talk about is the Big Bang, right? We're going to talk about this. So this was the formation of the solar system, right? So the Big Bang started right here. Okay, let's quiet down. The next thing that we had, and this was about 14.6 billion years ago. The next step was the formation of the solar system. And what was happening there is you started to have dust that was clumping up, right? And finally what happened is this collection of dust formed a disk. And those disks started to basically form planets. Because they were, in a disk you just have more clumping of stuff, like matter. So collection of dust. This formed a disk. And I'm skipping over a lot of details. I'm just trying to give you a broad overview of what's going on and what's relevant for your test, okay? These clumps became planets, okay? All right, so now you have all these clumps that are starting to form, right, around this giant disk. So we have this giant disk of just like stuff, and as time passes, right, soon this disk of dust, right, it's going to start becoming different planets. Cool. So time. Planets forming. So now we have this next event, right? This event right here is the formation of the moon. And this happened this is 4.57 billion years ago. Alright, so the next person to make that sound is going to get a detention. And I won't just give it to one person, I'll give it to those 4 people in the corner, okay? So it needs to stop. Alright, so now you know, whoever's doing that, make them stop, right? So now you have your warning. Okay, so the formation of the moon. 4.53 billion years ago. Cool. Now what happened is you had this giant Mars-sized mass called Theia, and right here it had a glancing glow with a very young Earth. And after that collision, you had this thing coming out that stayed in the gravitational pull of that young Earth, and that was the moon. Collision, and this was a glancing blow, right? Cool. All right, so now we have this molten Earth, right? Heavy bombardment is going on, so we can talk about that. Of Earth. Now, heavy bombardment was when we basically had a whole bunch of asteroids hitting the surface of the Earth. Okay? Now, why were these asteroids actually able to hit the Earth? There was something missing preventing them from stopping. That thing was the, I'll take a hand. It was the atmosphere. Yeah. Sorry, I didn't see your hand. Cool. So now you have heavy bombardment, right? And there's no atmosphere. Now that heavy bombardment is kind of nice because it's bringing all of these different pieces of metal and matter to Earth, so we can make it larger. Now, if you think about elements, right? If you think about heavy metals versus light metals, would you expect heavy metals to be towards the center of the Earth or towards the surface? And then where would you expect to see light metals? I'll take a hand. Yes.
Around the crust, the light stuff would be like that.
Exactly. So if you have the gravitational pull of the Earth pulling you inwards, if you have more mass, you're going to be pulled more towards the center. If you're lighter, you're going to not be pulled as much and you're going to end up on the outside. So right here, in the center, you're going to have your heavy metals, right? And on the outside, you're going to have these lighter metals. And the segregation is due to the difference in like mass, density, but also the effect that's going to have on gravity. So if you're heavier, you're going to go towards the center more. Okay, cool. There you go. Let's go ahead and keep on trekking on. Let me find the next piece of notes. So, I'll let you catch up. Here we go. All right. So, in the Earth's early atmosphere, you basically had no oxygen, right? So Earth's early atmosphere, the big things to take away from this. Had no oxygen. That is the biggest thing you could take away from this. But what it did have is it had hydrogen sulfide, methane, had ammonia. Now, it was a pretty toxic place, right? Now, in order for life to form, what is the first thing that needed to happen? Now you have all this water vapor in the air, right? What needs to happen for life to first form on Earth? Yes.
Oceans.
The oceans need to form. So what needs to happen to the Earth in order for the oceans to form?
It needs to separate. The continents to separate.
It needs to cool down, right?
Yep.
So Earth cools down. And because of this, water vapor forms oceans. And we know that there's all this poison gas in the air. It's not good for anything to survive. So what happens, right, is this water vapor is kind of your first membrane. It's this first blockade that basically prevents anything poison from getting to you. So for the first living organisms, this was a place for them to form. First living organisms. Now, some of the first living organisms were cyanobacteria. And cyanobacteria were cool because they could perform photosynthesis. So now, you have photosynthesis going on. That's a good thing. Now let's keep on talking, right? So if we were talking about a multiple choice question, I asked you, what life forms are most similar to early life? Some of those answers could include answer choices, right? Could include like dinosaurs, plants, vertebrates, right here, or it could be bacteria. So if I'm telling you this, what is most likely to be most similar to the earliest life forms? It's going to be
Bacteria.
good job. It's going to be bacteria. So the first life forms are most similar to bacteria. Cool. All right. The next thing we're going to talk about, right, is this. So once you have prokaryotes and eukaryotes starting to form, and just to let you know, prokaryotes came way before eukaryotes, right? What is the key difference between prokaryotes versus eukaryotes? I'll take a hand. Yes. Yes. There's one key difference.
Is it one multi-cell or something?
Ooh, right over here.
Is it that one has a nucleus and the other one doesn't?
Nailed it. Nice. So right here we can see that prokaryotes do not have a nucleus. No membrane-bound organelles, right? And a nucleus would be a membrane-bound organelle. And right here you do have a nucleus. Let me look at my notes really quick. Let me see if I'm missing anything. Let's see. Yeah, so the only thing, right, you could think about, so how do we form energy, right? So we're going back to, what do we store inside a nucleus? What is the type of thing that we store inside a nucleus? We store, yes?
The protons and neutrons?
Yes. I mean for a eukaryote. But yes, you're correct, if we're talking about atoms. So inside a cell, right, what does the nucleus contain? That's right. It contains DNA. So right here, this nucleus is going to contain our DNA. Okay, and just to jump back really quick, right? Some of the uses of isotopes are going to include carbon dating, treating cancer, just general marking, right? So those are some of the many examples of carbon dating. So this was a really rough description of, early Earth, but this was all the information that you needed for the relevant stuff on your exam. So with that, good luck. All right.